Good afternoon, and welcome to Research in Action, brought to you by Florida Atlantic University in the Division of Research. With that, it's my very great pleasure to welcome back Dr. Atta Sarajedini. Dr. Sarajedini is the Bjorn Lemborn Endowed Chair in Astrophysics here at FAU. Before that, he was the Dean of the Charles E. Schmidt College of Science, and before that, he served as Associate Dean at the University of Florida. Dr. Sarajedini received his Ph.D. in astronomy at Yale University and was assistant professor at Wesleyan University in Middletown, Connecticut before he went to UF. With that, I'm just going to have him tell you about his fascinating research on galaxies. Welcome, Atta.
Thank you very much, Karen. I'm going to go ahead and share my screen, and then we will start the presentation. I appreciate that introduction. So my presentation is going to focus on stars and what stars tell us about the galaxies in which they're located. But first, I want to start a little bit of the science part and just familiarize you with some of the notation that we use in science. And as you can imagine, we use some very large numbers in astronomy and very small numbers. And so we use scientific notation as indicated here to indicate large and small numbers. So 100, for example, is 10 to the 2, which basically means 1 with 2 zeros after it. 1,000 is 10 to the 3, 1 with 3 zeros after it, etc. So this is called scientific notation. And then secondly, just how we measure distances and various quantities in science. So these are mostly metric measurements, which aren't necessarily things we come across every day. But so, for example, meters, 1 meter is about a yard, a kilometer is 1,000 meters, and so forth. We measure temperatures in this crazy, wacky scale called kelvins, which has the same degree size as centigrade, but has a different 0 point, so that a room temperature, for example, is 68 degrees Fahrenheit, 20 centigrade, and 293 on the Kelvin scale. Now, in astronomy, we also talk a lot about the sky, obviously, what's in the sky, how large things are on the sky, and we measure things, the angular sizes in degrees on the sky. So from the horizon to zenith is 90 degrees, every degree is 60 arc minutes, etc. Distances, we talk about light years, and I'm going to talk about this more in the presentation. But 1 light year is the distance light travels in a year, which is 6 trillion miles, or about 9.5 trillion kilometers. So that's kind of some preliminaries to kind of get us all on the same page about how we measure things in astronomy and scientific notation. So before I actually delve into the science, I want to talk about what science is. What is science? How do we do it? What's it used for? Well, a simple explanation is that science is a tool to better understand the natural world. Now, how does it typically progress? Well, we ask a question. That's the first thing we want to do is ask a question. We then gather information or observations to answer the question. We look at the observations to try to understand what they're telling us about the question we posed. And we come up with an explanation to explain the observations. Another word for explanation is a hypothesis, a theory, or a model. And every good model or theory makes a prediction or predictions, which we can test with the observations. If the predictions come true, in other words, if the predictions and the observations are in line with each other, then we can say, well, the explanation is probably correct. If they don't, then we have to go back, modify the explanation. The predictions it makes are in line with the observations. And if they are, then we can be fairly confident that the explanation, also known as a hypothesis or a theory, is probably correct. So this is kind of the way science is structured and how it works. Now, I mentioned earlier about a light year and the distance light travels in a year. Well, the speed of light is 186,000 miles per second. Seems like a lot. It seems like it's really fast, and it is by our earthly terrestrial standards. But it's very slow when it comes to the size of the universe. So what that means is that the speed of light is not infinite. It is finite. It has a certain value. so that light from outer space takes time to get to us on the Earth. So for example, as I say here in the slide, the moon, when we see light from the moon, we see it as it was 1.5 seconds ago, 1.5 seconds in the past. The sun is 8 1/3 minutes away. So we see the sun as it was just over 8 minutes ago, again, in the past. So anything that's like up in the sky, we see it as it was in the past. And like I said, 1 light year is 6 trillion miles. So if we see something that's 1 light year away, we're seeing it as it was 1 year in the past. Looking out into space is looking back in time. I want to introduce you to a very important diagram in astronomy. And this is called the Hertzsprung-Russell diagram, or simply HR diagram. And if you just follow my mouse here on the screen, you can see that there are 3 properties of stars that are plotted in this diagram. Temperature, which is on the horizontal axis here, in units of Kelvin. Luminosity, which is the brightness of the star on the vertical axis. And radius, which are these dashed lines here. So this line, so the sun, for example, is at one solar mass. That's what this represents. And it's at about 6,000 Kelvin and 1 solar luminosity. The sun is right here where my arrow is. So a star that's 10 times larger than the sun in radius would be along this upper dashed line, and 100 times is that topmost dashed line. And 1/10 the size of the sun's radius would be the lower dashed line. And my point is that this diagram is the most important diagram in astronomy. Why? Because it takes the 3 main properties of stars, temperature, luminosity, and radius, puts them on the same diagram. So we can compare all 3 properties together at the same time. All stars ever observed fit somewhere in this diagram. Now, this gray line is called the main sequence. Why? Because it is the main sequence along which almost all stars are located in this diagram. Not only is it a main sequence, but it's also a mass sequence. Mass is another property of stars, and it's quantifying how much material is in the star, how much matter is in the star. And so on the upper left of the main sequence, these stars are 10 to 15 times the mass of the sun. In the middle is 1 solar mass, and in the lower right is tenths or a few tenths of a solar mass. So this diagram is full of information. It plots temperature, luminosity, radius, and mass of stars. And to understand how stars behave, which is the same as saying to understand how galaxies behave, this is our tool. This is the Rosetta Stone, if you will, of stellar evolution and therefore galactic evolution. We're going to use it in this talk quite a bit. So when I look at stars, real actual stars, I can plot them in this diagram as dots. And so we can actually use the appearance of the diagram to tell us how old stars are, and in particular, clusters of stars. So on the left, excuse me, on the left, here's a picture at the top of 2 star clusters, this one here and that one there. And the dots represent the temperatures and luminosities of the stars in these clusters. And you can see that this cluster, these 2, their HR diagram looks a lot different than, say, the one in the middle. This is another cluster. Here's its HR diagram. Again, temperature and luminosity, and looks different from the one on the right. This is another star cluster called a globular cluster. Its HR diagram, in turn, looks different. The appearance of these diagrams from the left to the right is largely indicative of the age of these stars. So on the left, these stars in this cluster are 10 million years old. In the middle, 500 million years old. And on the right, 12 billion years old. So for reference, the universe is 13.8 billion years old. So this cluster on the right is a substantial fraction of the age of the universe itself. So 10 million, 500 million, and 12 billion. And we can tell all those properties of the clusters by looking at the HR diagram. That's why I started with it because it's a very powerful tool to understand how stars behave and how they evolve. Now, that was kind of the background as far as the science. Now I want to give a little bit of a background in terms of where we stand, where we sit, where the sun sits in space, our place in space. That's what the next series of slides is going to give us a sense of. I find that there's confusion between the concepts of planets, solar systems, galaxies, and the universe. The next slides are going to put those in perspective. And this is an artist's conception of the solar neighborhood, where the sun sits in the galaxy. In the middle, of course, is the sun, and around it are depictions of the nearby stars. And this bar up here is 10 light years. So remember, this is the distance light travels in 1 year. That's 6 trillion miles. This is 10 of those. Some of the stars you might even recognize by their names. Sirius, Procyon, Alpha Centauri, that's the nearest star. Most of the other stars, though, you're not going to have heard of because they're relatively faint. So as we zoom out some more, we're going to now see more of the sun's neighborhood in the Milky Way galaxy. The sun's in the middle, and then we have even more stars as we zoom out. Now this bar is 100 light years across. Now we're going to zoom out some more, and this is 1,000 light years across. And what we see then are the spiral arms of the Milky Way galaxy. So this is an artist's conception of the solar neighborhood in the Milky Way galaxy. And there's some more stars here maybe that you recognize besides the sun, Betelgeuse, Rigel, Polaris, that's of course the North Star. And as we zoom out some more, you're going to see the galaxy as a whole. Sorry. This is the artist's depiction of the Milky Way galaxy, and it is 100,000 light years across. So this bar is 10,000 light years. From the left edge to the right edge of the Milky Way is 100,000 light years. We, at the sun, are about 25,000 light years from the center of the galaxy. When we look at the center of the galaxy, we're seeing it as it was 25,000 years in the past. Now, what you see also here are these dots. Those are the globular clusters, the picture of one of which I showed you a picture of earlier. And this is a dwarf galaxy orbiting the Milky Way. So this kind of gives you a sense of the scale of just the Milky Way galaxy. Now, you might ask yourself, well, we know how big the galaxy is, 100,000 light years across, but how many stars does it contain? How many stars are in the Milky Way galaxy? Well, the answer is 100 billion. 100 billion stars in the Milky Way galaxy. And that's just one galaxy of millions of galaxies that we know about and that we've located in the universe. Excuse me. This is another kind of depiction or artist's conception of the Milky Way. This is the edge-on view. This is the face-on view. And if I zoom into one of these globular clusters, that's what it looks like. That's what I showed you earlier. This is one of those clusters that's 12 billion years old, that was formed very early in the history of the universe and the history of the Milky Way galaxy itself. And then in the disk of the galaxy, right in the middle, we have these open clusters. I showed you this earlier also. This happens to be the Pleiades. The Pleiades is a few hundred million years old compared to 12 billion, which is one of these globular clusters, compared to 13.8 billion, which is the whole universe as a whole. So here's some more pictures of those, again, illustrating the power of the HR diagram to give us insight into the ages of these clusters. And remember, this is temperature and brightness on the vertical axis. This is the main sequence, and we can actually use the appearance of these diagrams to figure out how old these star clusters are. And by implication, the galaxies in which they're located, how old those galaxies are. This is a range of HR diagrams for different open clusters. These are individual main sequences for different open clusters. Again, this is temperature and brightness. Some of these maybe you've heard of. I showed the Pleiades earlier. The Hyades is a very well-known open cluster. And of course, the sun is here down here on the main sequence. So by measuring the ages of these clusters, we can actually put together and reconstruct the history of the Milky Way galaxy and different regions of the galaxy where those clusters are located. And so just taking two of these, 2362 and M67, I can show you pictures. Here's 2362. It's still enshrouded in the gas and dust that are the raw materials that made the stars that are inside this cluster. 5 million years old. M67, all the gas and dust are gone. They're made to use the star. They're made to produce the stars, and all that's left are the stars themselves. And you can see that the colors of the stars are somewhat redder than this cluster on the left. And this is an older system, about 4 billion years compared to the 5 million year old 2362. Now, how and where do stars form? Well, generally speaking, stars form in clouds of gas and dust. And I'm sure many of you have seen this picture. This is the well-known Eagle Nebula observed by the Hubble Space Telescope. This is the areas where stars form. And these little nodules up here, and these little tiny nodules, that's where stars form. And I believe the next slide is a movie showing you a bit of that. So let's watch that.
Newborn stars are found within brilliant, colorful nebulae. However, star formation begins in dark, dense clouds.
Alrighty, so that gives you kind of a big picture view of how we think stars and planets form. This one slide hopefully summarizes what that movie just said, but in a more contained and compressed form. So star formation starts on the left with different stages, and each stage takes a different amount of time. What to take away from this slide are the time frames. The entire process of forming stars, from these large gas clouds to the actual planets and stars forming, is about 10 to 20 million years. That's the rough time frame. And what causes this process to happen? One word: gravity. Gravity is the force that brings these gas clouds together, causes them to collapse, rotate, and then form stars at their very centers. And then what do we have after that? Well, we have stars. We also may have planets. And in many cases, there are planets that form around the stars. And this is just an example. In the lower left is our solar system today. And this may have been what the early solar system looked like. So the sun, the proto-Earth, proto-Mars, proto-Jupiter, and all this material, mostly gas and in this case a lot of dust and small planetary particles, came together to form what we have today, which is the solar system composed of the sun and 8 planets, asteroids, comets, and everything else that's in and dwarf planets and everything else that's in the solar system itself. Now, this slide kind of puts together the history and formation of the sun. Again, we're looking at everything in this diagram, the HR diagram: temperature, brightness or luminosity for the stars, The sun starts on the main sequence. That's where it is now at 0.7. In about 5 billion years, well, the sun is 4.5 billion years now, but in about 5 billion years, it will expand. It will become a red giant, going from the 0.7 to 8 to 9, and then 10 and 11, and it will engulf the entire inner solar system. The Earth will be inside the sun's atmosphere, the outer part of the sun. And then over time, the outer parts of the sun will be lost. What will be left is just the core, which is what we call the white dwarf. And that will basically be what's left of the sun after another 5 billion years of evolution. And all of that is summarized in this diagram on the left, in the HR diagram, and in kind of graphical and artist's form on the right, from the formation to today, with the sun becoming a red giant and then ejecting its outer parts and then becoming a white dwarf. This is what the sun will end up as in about 5 billion years. Now, why do we care about this? Because this is the evolution of a one solar mass star. If we can understand how stars of different masses evolve, then we can actually study stars in different parts of the galaxy and figure out how old is the galaxy as a whole, and how do the different parts of it come together, in what order, and how did it form over time. Now, stars that are more massive than the sun, the ones that are, say, 10 or 20 or 30 times the mass of the sun, don't just become white dwarfs in this very quiescent, kind of calm process. They actually explode in what are called supernova explosions. And this, some of you may recognize this. This is called the Crab Nebula. It's the constellation of Taurus, and it is what's left over from an exploding star that exploded in the year 1054. And how do we know it's exploding? How do we know that it's expanding? Because we can actually measure the expansion of the Crab Nebula over time. This is 100 years of time-lapse pictures of the Crab Nebula expanding over time. And you can see clearly that it is expanding, that the material, the gas, and there is some dust, but mostly it's gas, is expanding over time. How do we know that it exploded in 1054? Well, because we can measure the expansion rate of this nebula and ask the question, how long ago, at that expansion rate, was everything down at one point at the very center? And that answer is 1054 AD. So that's how we calculate how far this thing has expanded and how long ago it began the expansion. The supernova explosion happened in 1054. Now, getting back to this, so I left off here with the Milky Way galaxy and our artist's conception of what the galaxy looks like. Now, let's go further out. Let's actually look beyond the Milky Way. The Milky Way is now in the middle. This is 100,000 light years, this bar. And now we begin to see dwarf galaxies that are orbiting the Milky Way. These are dwarf galaxies. They're small. They're low mass. The Milky Way is 100 billion stars. These galaxies might be 1 million, say, or 10 million stars each. They're small. You might think of them as the building blocks of larger galaxies like the Milky Way. And some of them you may have heard of if you're an amateur astronomer, maybe you've heard of some of these names. But let's step out again. And now we see even more of them. And not only that, but we actually begin to see the local group of galaxies, which includes the Milky Way, Andromeda, the Triangulum Galaxy, and a whole host of other dwarf galaxies. So the local group is mainly composed of the Milky Way, Andromeda, and a whole couple of dozen dwarf galaxies that you can think of them as leftovers from the formation of the larger galaxies that you see here. And now this bar is 1 million light years. And we are still just in the local group of galaxies that make up the Milky Way system. We're still really nearby. Now, I want to talk about where the elements and where the chemical elements came from. I'm sure you've all seen about this periodic table of the chemical elements where hydrogen and helium are the two simplest. They came from the Big Bang, the process that started the universe, mainly produced hydrogen and helium. The question is, all the other elements on this table, carbon, nitrogen, oxygen, phosphorus, sulfur, chromium, vanadium, where did they come from? If the universe started with just hydrogen and helium, where did everything else come from? Well, as it turns out, in astronomy, the origin of all the other elements is linked together. They are all connected by similar processes that produce them in different locations and environments in the universe. And so because of that, we call all those other elements metals. Now, a chemist would probably cringe at this because they're not really all metals in the chemistry terms. But for astronomy, because all the other elements heavier than helium are produced in very similar ways, basically in stars, we call them all metals. So what that says is that at the beginning, Big Bang, there were no metals, essentially zero. And over time, as the universe evolved and stars formed and produced elements inside them, the metal content of the universe increased. What that means then is that there's a direct correlation between time and the metal content of galaxies. Now, it's not perfectly correlated, it's not one-to-one, but generally speaking, there is a strong correlation between how old a galaxy is, or a star, and how metal enriched it is. So this is the Andromeda Galaxy, as I mentioned earlier in the artist's conception. This is the nearest large galaxy to us, the nearest large galaxy to the Milky Way. Andromeda is 2.5 million light years away. What that means is the light we receive from it today left it 2.5 million years ago. It has, in this picture anyway, you can see two dwarf galaxies that orbit Andromeda, M32, which is this fuzzy thing here, and NGC 205, which is this one up here. Think of these dwarf galaxies as satellites of the Andromeda Galaxy. They're orbiting the Andromeda Galaxy. Now, these satellite galaxies are actually quite common in the local group, as I showed you earlier in that artist's conception. These are now some pictures of these dwarf galaxies. Some of them are actually kind of boring. I mean, there isn't much to be said, for example, about this one on the left. Others are more interesting. They have gas and dust in them, like this one in the upper right. This galaxy is a dwarf galaxy. It's about 1,000 times less massive than the Milky Way, but it has its own young stars in it that are forming. And how do I know that? Because we can actually measure the temperature and luminosity or brightness of the stars in this galaxy. We can make an HR diagram of those stars and calculate the age of the stars in that galaxy, and therefore know when that galaxy formed. So by looking at the HR diagrams of these galaxies and looking at where they are in the local group, we can reconstruct the formation history of the local group of galaxies. It's really quite a powerful technique. Now, what have we learned about some of these dwarf galaxies? Well, some of them are like this. They're kind of just hanging out in space, minding their own business. But some of them are actually interacting with the galaxy that they're orbiting around. So, for example, this, let me see if I can play this video. This is an artist's conception of our Milky Way, right here in the blue stars. There's the sun right there. And these orange stars are, or were, a dwarf galaxy that interacted gravitationally with the Milky Way in its orbit. I'm going to play the video. It's going to show you a pan out of, or pan around of this Sagittarius dwarf galaxy to show you the actual shape of the galaxy in three-dimensional space. So this is a dwarf galaxy that was on its own, minding its own business, and it got too close to the Milky Way. And when it did, the gravitational pull of the Milky Way galaxy distorted the Sagittarius dwarf into what it looks like today, which is composed of these orange stars that are distributed all around, the outside parts of the Milky Way galaxy. The point is that this kind of interaction is quite common. Many dwarf galaxies interact with their parent larger galaxy and become disrupted and distorted and distributed, really, along their orbit in space. And so when we think about this, we can get the ages of the stars in these dwarf galaxies with the HR diagram. And we can reconstruct the orbit of this dwarf galaxy and how and when in the past it did most of its interactions with the Milky Way. So this is going to be important because, okay, I better be careful. I don't want to give away the punchline, but this is going to be important because this process of galaxy disruption is essential to how galaxies form in general. All right, so I just basically said that. And so on the left, you can see this is a galaxy outside local group. It's quite far away, but if you look closely at it, it does have spiral arms, but also has this material coming out on the side, and there's this arc of material coming out from that, and there's even some very low-level stars and things on the left side. And so this is another example of a galaxy outside local group that has disrupted possibly a dwarf galaxy that got too close to it. Now, this is another movie over here on the right that illustrates, again, this is a simulation using just particles on a computer and simulating how a dwarf galaxy would look in the ideal world, if you will, as it interacted with the Milky Way. So I'm going to start the video. So here's the dwarf galaxy. And the law of gravity predicts that as this object orbits the Milky Way, it gets disrupted and distorted and over time destroyed by the Milky Way's gravitational field. So the idea is that the Sagittarius dwarf, which I showed you the real data for in the previous slide, got that way because of this kind of interaction with the Milky Way. Once again, just to reiterate, we can measure the individual ages of the stars in these galaxies by putting them in the HR diagram. Now, you might ask, well, if one galaxy is doing that in the Milky Way, one dwarf galaxy, maybe the entire Milky Way halo, the spherical part, is made up of thousands of these disrupted dwarf galaxies. And if that's the case, well, then this is what the Milky Way halo would look like. So the galaxy, Milky Way, is in the middle, and all these different colored arcs are the remnants of disrupted dwarf galaxies that have interacted with the Milky Way in the past. Now, this is the model. It's not; these are not observations, but this is a model. And getting back to the scientific method that I mentioned earlier, our model is only as good as the predictions it makes, and whether those predictions come true compared to real life. And that's the point. Do we actually see this in and around the Milky Way galaxy? And we can actually test it by looking at galaxies with the Hubble Space Telescope over time. So what this shows is these are HST, Hubble Space Telescope observations of galaxies nearby, which is on the left. And of course, nearby means today. As I said, the speed of light is finite, so when you look far away, you're looking back in time. And so on the left are nearby galaxies. That means the ones that are present today after the universe is 14 billion years old. And then going to the right, you see we have galaxies 9 billion years, 5 billion, and 2 billion after the Big Bang. So what do we see? Now, if I was in a live audience, I'd be calling on you. So be thankful we're not live, we're on Zoom. But what do we see here? We're gonna do science with our eyes. And on the left, we see galaxies that are the way they look today. On the right, we see them as they were when the universe was very young. How are they different? How are the galaxies on the left different than the ones on the right? Just the way they look. Well, one of the ways they're different is that they're smaller. the galaxies on the right are smaller than the ones on the left. That's one way. Another way they're different is that the galaxies on the right are less organized. They're kind of more patchy and more distorted, kind of just not really well put together, let's say, than the ones on the left. So what does this argue? Well, if we think of the galaxy sizes, it argues that over time, large galaxies formed from smaller ones. That we had small galaxies, dwarfs, if you will, that collided with each other, combined, and then over time mixed together and became the galaxies we see today, which are the ones on the left. We have this process then of forming galaxies from smaller to larger, from disorganized to organized. That's what this slide and some of the slides earlier I showed support, that model or that theory of galaxy formation. Now, I want to change gears a little bit and talk about some of my work in this area. And what I do to study galaxy formation is to look at stars that vary in their brightness, so-called variable stars. And this is actually an animated GIF showing you the stars in this globular cluster that are varying in their brightness. If you look closely, I'm not sure how much of this comes through by Zoom, but you can see a number of these stars are getting brighter and fainter. They're varying in their brightness. What they're doing in real life is they're getting larger and smaller in their radii. And as they get smaller and larger in radius, they get brighter and fainter in their brightness, in their luminosity. These are called variable stars. They're the linchpin of many areas of astronomy because they're easy to observe relatively, and their behavior, their brightness, their variation is indicative of their physical properties, one of which is age. And again, this is part of one of the tools that I use to study galaxy formation are these variable stars. And so what we can do is we can construct what are called light curves of these stars. And these are multiple light curves. So in each panel, on the horizontal axis is time, on the vertical axis is brightness. And these are individual measurements of the brightnesses of these stars over time. And these variable stars, you can see they're clearly getting brighter and fainter in a very regular way. We can measure the periods of these variable stars and use those periods to understand the properties of the stars and in turn, properties of galaxies in which they're located. And look at these are the periods. These are in units of days. So this would be about 4/10 of a day or half a day is how fast this star is varying. Remember, these are actual stars that are getting brighter and fainter in half a day. These are stars that are getting brighter and fainter in a half a day. Imagine if the sun was like that. If the sun was a variable star like these stars, the Earth would be uninhabitable. There'd be no way for life to evolve to where it is now if the sun's brightness changed by this much, a factor of 2 or 3 in half a day, because the Earth would just be no place for life. So thankfully, the sun is not one of these stars. But thankfully, these stars exist because we can use them to study the galaxies in which they're located. And I didn't say it, but these particular stars are located in the Andromeda galaxy. These stars are 2.5 million light years away. And we can measure them and characterize their variation using the Hubble Space Telescope. And of course, when Webb starts looking at these stars as well, we'll be able to use the Webb telescope to study variable stars that are even further away than the Andromeda galaxy. So these particular types of stars are called RR Lyrae variables. I actually wrote an article about them for Astronomy Magazine in July of 2020. This is the cover of the issue itself if you're interested in getting a copy of it. This is July of 2020. It was a special issue just about stars. And I wrote an article that appeared in this issue about these variable stars and why they're important. I like to call them the Swiss Army knife of astronomy, because these kinds of variables, and as I said, they do this, they get brighter and fainter. in their luminosity. And if we can identify them, then our Lyrae variables are important, because just identifying them means that whatever galaxy they're located in has to be old. And by old, I mean at least 10 billion years old. By measuring their periods, we can actually measure how much metals they have in their composition. I mentioned earlier about the metals, about those are the elements heavier than helium, and they're an indicator of how chemically enriched the galaxy and the star is based on the time and how old it is. So our Lyrae, these variable stars, by measuring their periods, we can actually calculate how metal enriched they are, and therefore determine the metal enrichment of the galaxy in which they're located. I also mentioned that they are standard candles, which means that if you can identify one, you can actually calculate its distance from the Earth very easily. And in astronomy, distance is one of the holy grails of knowledge that we have to have about the systems we're trying to study. And then finally, I haven't mentioned this concept, but reddening is a very important problem in astronomy. When you look out into space, there's dust between us and other galaxies and other stars. That dust causes the light from those objects to appear redder than it actually is. And the color of an object is a measure of its temperature. So if we want to measure the temperature of an object, we have to know what the intervening reddening is, or else we'll get the wrong temperature. And our Lyrae are essential to calculating the reddening in the line of sight to a particular galaxy or star cluster that we're observing. So this is why I call our Lyrae the Swiss Army knife of astronomy, because they have these multiple uses and multiple features. Now, what have we learned then so far using all these techniques, all these tools to tell us about the formation of galaxies? Well, all of that is summarized in this one slide. This is now our place in time and space. On the right is today. On the left is the beginning, the Big Bang. And as we go from right to left, we're looking further back in time, 13.8 billion years into the past. And one of the questions we really want to know is, when did the first stars form? After the Big Bang, 13.8 billion years ago, when did the first stars form? This slide says 400 million years, but this number could easily be 300 million or 200 million. We really don't know. And that's one of the big questions of galaxy formation is, when did the first stars, first galaxies form? And since then, when did the first planets form? Along with the stars, planets form, and the question is, how old is the oldest planet that we can find? We're still looking and trying to answer that question. There's a lot more in this slide than just that. I don't have time to talk about it. If there's a Q&A about this slide, I can discuss it more. But for the moment, let me just finish up with this slide, which is my last slide, advertising the podcast that I do about astronomy and the radio show that I did in Boca Raton last year called Science Rocks. On the left is the podcast. It's called Astronomy Minute. It's on Spotify, Google, Apple, and all the episodes, it's 175 episodes, are organized at this website. If you go to that website, it organizes all the episodes in topical form. So depending on what you want to listen to or what you want to learn more about, you can click on the link and you can play the podcast. Every episode is not more than 2 minutes long. So it's in small, digestible chunks. And it's free and there are no ads. On the right is the radio show that I did in Boca Raton last year. It's also archived on this website. It's a combination of rock music, discussions about astronomy, and I also interview a number of different scientists in different areas of science that are associated with FAU, Nova Southeastern University, and other universities that I could contact. But both of these are available online at these websites, and you're welcome to click on them and check them out and listen to the episodes. All right, I will stop there. I thank you for your time, and I will take any questions. Should I stop sharing my screen now, Janelle or
Sure.
Karen?
Yes, yeah, that'd be great. Thank you very much, Atta. That was very fascinating. We already have a number of questions that our audience submitted. As a reminder, if you have a question, please use the Q&A button at the bottom of your screen and type your question there. We're going to try and go through as many as we can in the remaining time. Those questions that get unanswered, are left unanswered, we're going to ask Dr. Sarajedini to answer offline, and we're going to post the answers together with a recording of today's presentation on our website. So just look for Research in Action at FAU. Okay, apparently we do have a class, Ms. Arb's class, participating today, and the class would like to know how scientists are able to measure the temperature of the stars if they are so far away.
It's a very good question. And in fact, let me preface my answer by saying I encourage everybody on the Zoom call who listen to my talk. I encourage all of you, whenever a scientist tells you something, your first question should be, how do you know? How do you know? And that person ought to be able to explain, how they know whatever they're trying to tell you. So what this question has to do with is the temperatures of stars. How do we know the temperatures of stars? Well, if you go out at night, look up in the sky, and assuming it's clear and you have a fairly dark sky, you'll notice stars have different colors. Some of them are red, some of them are yellow, orange, maybe, some are blue. Those colors represent their temperatures. Now, let me ask you this. When you go to the bathroom and you're ready to wash your hand and you have you don't have an automatic faucet, but you have one with knobs, and you're trying to get the hot water. Right? So what color do you look for when you want hot water? Well, you look for red, right? Unfortunately, that is the opposite of nature. Red stars are actually the cooler ones. Blue stars are the hotter ones. So we can use the colors of the stars to measure their temperatures. And in particular, we have a way to convert color with, red or blue or yellow to a quantitative measure of temperature. We don't say it's hot or cold. We actually can say that red corresponds to 3,000 degrees Kelvin, or blue corresponds to 20,000 degrees Kelvin, or something like that. So mainly the answer to your question is the color of the star represents its temperature.
Thank you, Atta. Okay, our next question. Are star clusters defined simply by proximity with an arbitrary amount of space between one cluster and another, or is there some other force that defines or maintains the star cluster?
That's actually a very good question, because at the moment in astronomy, there's a controversy about exactly how do you define a star cluster. And the primary definition is that we look for stars that are literally clustered together in the sky. They're in very close proximity to each other in the sky. And when we define what close proximity means, then we call that a star cluster. And if we call it a star cluster, then by definition, the stars are held together by the force of gravity. They move through space together, and they evolve together. They were formed together at the same time. And we can go back and, of course, measure their motions, confirm they're moving through space together, confirm that they're gravitationally bound to each other. We can do that after the fact. But the first kind of step is to define what stars are in close proximity to each other, and then start from there, and move then from that to, are they associated with each other gravitationally?
Well, it's very complicated. You mentioned the Big Bang at the end of your presentation, Atta. The question here is, what happened before the Big Bang? Do we know?
So that's a good question. And the answer is no, we don't. Because science, the first step of doing science is gathering observations, getting data. And in astronomy, most observations are in the form of light. We measure the light output of stars, of galaxies, planets, whatever. And we have no way, at least yet, of measuring light from before the Big Bang. Because at the Big Bang, everything was compressed into one point, and before that, there is no light coming to us from that time. So we have no way of knowing, scientifically at least, what was there before the Big Bang. Now, do we have a way of knowing? Well, that's up to you. Depends on what you mean by knowing. Many people like to philosophize about what was there before the Big Bang, and if you are if you're a philosopher and you believe that philosophy is a way to the truth, then you can philosophize all you want about what was ever before the Big Bang. But science is at a loss to, to help you with that answer.
Maybe eventually we'll find out. Coming back to your presentation, Ada, and the metals that you mentioned, right? So since the periodic chart or periodic table reflects the metals or elements that are found on Earth, does that mean that older planets may have metals or elements that we don't find on Earth?
Yes, it could be. But my understanding is that every element in periodic table we have found on the Earth. Now, some of them are more common than others. You're going to have a lot more, say, carbon than you will, phosphorus, because carbon is so common. And even helium, was first discovered in the sun. That's where the word helium comes from, helios.
Right.
So all those elements we've discovered on the Earth. Now, I think maybe the questioner is asking, are there elements that we don't have on the Earth that we could observe or discover on other planets? Possibly, but we would not know how to find them because
or characterize them, right?
or characterize, right?
Yeah.
Because every element we know of is all the ones on the Earth.
Yeah. A related question: how do you measure metal enrichment?
Right. I didn't talk about this. One of the things that we can do to light, when we measure light from other objects like stars and planets, we can look at the different colors of that light. All light is composed of different colors. And when you look at the distribution of the colors, you can actually measure that distribution. How much green light is there? How much yellow light is there? How much, red light is there? Based on how much of that light there is, we can use that distribution of colors to measure the presence or absence and the amount of certain elements. And I don't have a slide here to show you, but this process is called spectroscopy. And you can use the distribution of the colors or lack thereof to infer the presence or absence of certain elements in the composition of stars. And you can say this particular star has a lot of carbon in it, or a lot of iron, or a lot of oxygen, or no nitrogen, or very little hydrogen, that kind of thing. And we can do it quantitatively. That is to say, we can measure the mass of that element in that star.
Thank you. Switching gears a little bit, what do you feel is the best candidate for explaining dark matter?
Oh, yes. So, well, let me first ask, what is dark matter?
Mm-hmm.
Not what is it composed of, but what is it? Well, we don't know. We do know two things about dark matter. It's matter and it's dark. That's it. Now, what does that mean? Well, matter is material that has gravity associated with it, and dark means it doesn't give off any light. So whatever it is that is actually the composing dark matter, it has to have gravity and it cannot give off any light. Now, my personal opinion is it's a combination of all different types of matter that are dark. So, for example, black holes. Black holes are they're dead stars that are just basically dark. It's a combination of black holes, of neutron stars, and possibly just different kinds of exotic particles we haven't characterized yet. So I think there's actually a number of different possibilities with respect to what dark matter is. It isn't just one thing. It's a whole lot of different things that are all dark and matter.
Interesting. Okay, we're almost out of time. I'm going to finish us off with one last question. There are more questions, Ada. We will send you the questions offline, and please look out for the answers in a few days on our website. Again, it's FAU Research in Action. If you Google that, you should find the website. Okay, our last question for today. Does the size of the planets in our solar system reflect their birth order? For example, is Jupiter the first planet that was formed in our solar system?
Short answer is no.
Okay.
There is no relationship between the size or mass of the planets and when they were formed. Generally speaking, it's actually the other way around. The smaller planets formed first and the larger ones formed later.
Okay.
So it takes longer to accrete the material, onto the the seed, if you will, of the planet formation to start forming a large planet. Generally speaking, also, having said that, generally speaking, the inner planets are going to be the ones formed first. That is to say, Mercury, Mars, Venus, and Earth. And the outer planets are going to be formed next, Jupiter, Saturn, Uranus, and Neptune. So overall, there is no relation, though, between the size and which was formed first.
Interesting. Okay, I lied. I'm going to ask one more question.
Yeah.
So you talked about the Hubble telescope, right? And more recently, we put the James Webb telescope into commission. Can you speak a little bit about what the Webb telescope can do that Hubble couldn't?
Yeah, definitely. Webb, of course, is a larger telescope. The Hubble telescope is 2.5 meters. The main mirror is 2.5 meters across. Webb is 6.5 meters, which means it'll be able to see much fainter. And in my presentation, I talked about looking out into space, looking back in time. Well, looking out into space, looking back in time are the same as looking at very faint objects. The further away you look, the further back in time you look, the fainter the objects are. So the Webb telescope, because it has a larger mirror, will be able to see further away, further back in time, and fainter. So one of the main goals of the Webb telescope is to actually look further away, back in time, and find those first stars formed after the Big Bang. That's one of the major, if you will, missions of the Webb telescope. The other thing I want to point out quickly is that Webb is optimized to observe the very red light, much redder than what your eye can see, what we call infrared light. So infrared light is more amenable, let's say, to looking far away and also looking into the dust, into the areas where planets are forming. So Webb's going to be able to tell us more about how planets form that are enshrouded in, the dust and the gas from which they're forming right now. So Webb's main thing is early universe and the formation of planets, which Hubble cannot do because it can't look in the infrared.
Fantastic. Very, very fascinating, Atta. Thank you very much for joining us today. Again, we will send you the remaining questions and ask you to answer those offline, and we will post those on our website together with a recording of today's presentation. Thank you, everybody, for calling in. We hope to see you next time. Have a great rest of your day. Bye.
Thank you.